we're going to talk about linkages and the kinematics of linkages. We'll cover things such as Grashof conditions, degrees of freedoms, and a classification of the types of mechanisms. So before we move on to what a linkage is, we need to discuss and understand what a degree of freedom is. So a degree of freedom is the number of coordinates needed to define the position in space. So in 2D space, there are 2 coordinates that need to define a point, not a body, but a point. In 3D space, there are 3 coordinates that need to define that point, not that space. If we start talking about a rigid body, a single rigid body in 3D space, we need to define 6 degrees of freedom. So this is an x, y, and z location, often tx, ty, and tz, and then a rotation x, rotation y, and rotation z. So these are the 6 degrees of freedom that need to be defined in order to uniquely define a position in space. In 2D space, I want you to think about how many degrees of freedom need to be defined. When we talk about degrees of freedom in the context of machine design, a degree of freedom, and some textbooks will use the term mobility. These are interchangeable. This defines the number of inputs needed for control. Okay? So the number of inputs needed for control basically uniquely defines where a point is in space. A simple example here would be if I've got a very low technology backhoe, okay, and I need to define what this point is right here, x in space. I've got 3 degrees of freedom. I've got the angular position of this arm, the angular position of this arm, and the angular position of this arm. Okay, so we'll call it theta 1, theta 2, and theta 3. So this system has a degree of freedom of 3. Okay. Another important vocabulary word, a bit of terminology we need to understand is a mechanism. It's a collection of links and joints to provide some sort of controlled motion. And in this case, we're assuming that the links are massless and they're rigid bodies, meaning there's a 0 deformation. Now this is a little bit different than what you likely talked about in ME201 when you did dynamics. And we don't want you to ignore that, but in the context of kinematics and kinematic design right now, and mechanism design, we're going to make this assumption. So a linkage. A linkage consists of links. Okay? And links are individual parts of that linkage, and they're rigid. A frame or a ground is a special case link, and that's a link that does not move. A joint is a connection between links. So in this case, what you'll see here is there's a pin right here. There's a pin here, and there's a pin here. Okay, so those are 3 joints. Okay. And then actually there's a sliding mechanism right here. So this is a sliding mechanism. That is also a joint. That's a translating joint. Okay, and we'll talk more about this later. And then a linkage is a collection of those links. Now, what this is right here is what is often called a toggle clamp. Okay. And this is a basic example of a linkage. what we want to take from that real-life toggle clamp or a real-life mechanism is a kinematic diagram. Okay, and a kinematic diagram is similar to a free body diagram. Okay, so similar to a free body diagram. A kinematic diagram allows us to focus on the geometry and the motion, velocity and acceleration of the mechanisms that we're designing. So what you can see up here is this is a real system. There's a linkage in here, and when we extract that out, we end up with a kinematic diagram that looks something like the following. What we end up here is numbers. Numbers refer to links. Letters starting at A refer to joints. And then typically letters starting in the latter half of the alphabet refer to points of interest. Okay, so we've got numbers are links. Letters are joints. And then letters are also points of interest. Okay. This is a kinematic diagram. It ignores some physical aspects and elements of the real physical part. Within the context of the kinematic diagram, we have different types of links. So a binary link. A binary link has 2 joints, one on each end. A ternary link, 3 joints, and a quaternary link, 4 joints located in it. We've got some joint types here. Joint types, we've got a revolute joint. So this revolute joint only allows rotation between the pink and the gray link. A prismatic joint allows sliding between the pink and the gray links. Okay, these 2 joints are or enable 1 degree of freedom. We've got a pin and slot, so you can imagine that this pink link could slide left and right as well as rotate. So this is a 2 degree of freedom system. We've got a link pressed against a plate, okay? And if we assume that this pink link can only move to the left and right here, not in and out of the board, this also is a 2 degree of freedom system. Okay. We've got some other types of joints here. A cylindrical joint, so we've got a shaft inside a block. This is a 2 degree of freedom system. A helical joint, or what you might know as a screw joint, is a single degree of freedom system. And the reason why it's a single degree of freedom system is as I rotate or count the number of rotations of this screw, I precisely know where this screw is. Spherical joint, we can rotate in 3 axes, but we cannot translate. And then a planar joint, we can move in 3 directions. So those are some joint types. The common joints that you'll see within this class, and really a lot of applications, will be these joints here. Further, we're going to see these joints a lot because we're going to be in planar space. And you guessed it, it's a plane, not a 3D space. So some kinematic diagram notation. These are examples of real physical links that exist in space. And here's how they would be drawn in a kinematic diagram. So we've got a simple tie rod, and this tie rod does have some volume to it, but in a kinematic diagram, we're going to draw it as a line with points. We've got a bent tie rod or a bent connecting rod, and we could draw it similar to this one, okay? But we draw it as a triangle because this is the space in the middle here over which this connecting rod takes up. Okay, we've got a ternary joint, so we've got a ball joint here and a ball joint on the bottom, and then a revolute joint here. So here's what our ternary joint looks like. And then here we have a type of joint. Okay, this is what we'll call a double shear joint. And in this double shear joint, we're going to ignore the fact that it's double shear and just draw it as a link with a joint to another link. Okay. Some additional notations. Okay, so we see a sliding V groove here. That V groove holds this block in alignment with the base block, but in a kinematic diagram notation, what we draw it as is just a translational joint. We've got a cam here. There's a joint actually between the cam, which is link 2, and the follower, which is link 1, and we're going to relate it or draw it as this type of joint. We've got a gear train or a gear meshing, so there's some stuff happening up here, and we can actually draw that very complex joint as just two circles that basically have a no-slip condition. Okay, so those are joint types and link types. I'll pause here. This is not an exhaustive list of notation. We'll go over some examples in class. We'll take a break here and pick up next time with constructing kinematic diagrams.